So today we extend what we talked about yesterday in terms of approximating the area under a curve using rectangles, and we formalize it a little bit more. So yesterday what we did was kind of like, felt like we were just doing random things, and how do you know to do that, right? Okay, so today we're going to give it a little bit more formal language, which might make it a little more confusing, but hopefully in the end, as we practice, it'll be a little bit easier to understand, okay? So the first thing is to define two types of sums, okay? First we have an upper sum and we have a lower sum, okay? And by definition, our upper sum is the sum of all of our triangles that are circumscribe the curve. So circumscribe mean go above or over the curve. And then our lower sum are all the rectangles that are inscribed in the curve, okay? So they're below it, okay? So upper sums and lower sums are what we're looking at. And by definition, a lower sum will always be less than or equal to an upper sum. They can never be reversed, because then by definition it would be switched, okay? They could be equal if, particularly if you have like a straight line, that would be, you would end up with them equal.
So the upper sum, like when you write the formula, it's always like capital or
It doesn't matter.
oh.
Well, oh, I'm sorry. Okay, so yes, I see what you're saying. All right, so this is the notation we use, okay? So the lower sum, yes, we do use a lowercase s for the lower sum and an uppercase s for the upper sum. And you'll note that what goes in here is the set of x values that are lowest for each interval. So depending on the kind of function you have, that might be the right endpoints, it might be the left endpoints, it might change actually depending on the function, right? If the function is increasing, the lower sum will be the left endpoints. If it's decreasing, okay, so if we got something like that, it's the left endpoints, okay, are going to be the lower sum. Oops, sorry, lower sum. And if it's if it's decreasing, okay, the lower sum is going to be the right endpoints, okay. So left or right depends on the function, but lower sum is always below the function, upper sum is always above, okay. And the key thing here is that the actual area, okay, which is ultimately what we're looking for, will always be between the two sums. And you might remember back to what things that we've done before, where if we have between two things, what we do to find the actual thing is take a limit. So that's where we're headed, okay? So the first thing we need to understand is how to find these upper and lower sums. Then we're going to use some limits to find the actual area. Okay, so example 4, we're going to do something similar to what we saw yesterday, except now we are not going to use a particular number of intervals, okay? We're going to assume that we partition our function into a certain number of intervals. Partition means like putting a wall up, okay? So a partition is breaking it up into pieces. So let me sketch our function here. Whoa, dropped my pen. Okay, so a partition means break it up. This is x squared, nice easy function, 1, 2, 3, 4. All right, looks like that. And we are looking for the area bounded by the graph of x squared, the x-axis, and between 0 and 2, okay? So I'm going to shade it in a little bit here. Okay, this blue or purplish area is what we're looking for ultimately. Okay, and in order to do that, we're going to use both upper sums and lower sums. And note here, we were not told how many rectangles to cut this into. So for now, I'm just going to do 4 just for the sake of our visual. Okay, so if we're looking at upper sums, it's our right endpoint is going to give us an upper sum. Okay, so there's a rectangle, there's a rectangle, there's a rectangle, there's one. Okay, and our left endpoint is going to be our lower sum for this one. So the first one will be just 0, second one there, the third one there, the fourth one there. Okay, so hopefully we can see that. Okay, so we've got 2 sets of rectangles we're going to look at. And once again, I drew 4, but we are going to partition into in subintervals. And we are going to assume that each subinterval is the same width. You don't always have to do that, and we'll talk more about what it means to not do that later. But, okay, we're going to assume that each one is the same width, okay? And if we do that, okay, then the width of each of them, we're going to call it delta x, okay, will be equal to the end points, which we call generally A and B, so the later endpoint B minus the earlier endpoint A, divided by n, the number of rectangles we divide into. Okay, so that's our partition. So in this case, B is 2, A is 0, and n is n. We don't know how many things we're dividing it into. We just know we're dividing it into a bunch of things. So n is our number of rectangles. Okay, and so our delta x, the width of each one, will end up as 2 over n. Okay, we're going to leave that there. N is going to act like a constant, even though we could plug different numbers into it. Okay. All right, now let's come up with expressions for our left and right endpoints. Okay, always our left endpoint, if we start at 0, okay, is our delta x times I minus 1. Okay, if you don't start at 0, it has to shift a little bit, but when we start at 0, it's delta x times I minus n. And our right endpoints are always delta x times I. Okay, and now we know that's always left and right, but that doesn't necessarily tell us which one's upper, which one's lower. Again, in our case, right is upper, and left just happens to be lower, okay, because it's an increasing function. All right, so now we have our delta x, our width of each one. We have our expressions for each endpoint, which let's go ahead and plug in. Delta x is 2 over n, okay, so this is 2 over n times I minus 1, and 2 over n times I. So now, our lower sum is going to look like this. Lowercase s, s of n, it's a function of n, it's a function of the number of rectangles, is the sum from I equals 1 to n of our function at these set of values that represent our the lower rectangles, which is 2 over n times I minus 1, times our width, which is delta x, which is 2 over n. Okay? Now that we have that, we can plug in the 2 over n I minus 1 into our function to get the sum I equals 1 to n of our function, which will just square all of that. 2 over n I minus 1 all squared times 2 over n. Oops, sorry, I wrote 2 over 2. 2 over n. Okay. All right, and from there, the rest is algebra, okay? We want to rearrange so that we get our I terms by themselves, okay? So we're going to have a 2 over n squared times 2 over n, which will be 4 times 2 is 8, over n cubed, okay? And then that can factor outside of the sum. All of the other terms do involve I, so they have to stay inside the sum. All right, and we're going to be left with an I squared minus 2I plus 1. Okay, and that's inside the sum. Now we can break that up into separate sums. Okay, so our 8 over n cubed stays factored out front. And then we have the sum of I squared minus 2 times the sum of I plus the sum of 1, which I'll go back. I equals 1 to n, I equals 1 to n, I equals 1 to n. Okay, so now we have 3 sums, and these are simple sums we can use our formulas to evaluate. Okay, so 8 over n cubed stays out front. Okay, the sum of I squared, our formula for that is n times n plus 1 times 2n plus 1 over 6. All right, so that's that. All right, and minus 2 times the formula for the sum of I, which is n times n plus 1 over 2. And the last one is just n, right? 1 times n, which is n. Okay, so these brackets are everything that's multiplied by 8 over n cubed. Okay, simplifying that, it takes a little bit of work, a little algebra work. I'm going to skip over that a little bit. But simplifying that, we can get down to 4 over 3n cubed times 2n cubed minus 3n squared plus n. Okay, distributing that, we're left with only one term that doesn't have an n in it. 8/3 minus 4 over n plus 4 over 3n squared. And let's think about what that means. What is n again? What does n represent?
Like how many
Number of rectangles. Okay, and the number of rectangles. So the only part of this lower sum, remember this is our S of n lower sum, that doesn't depend on the number of rectangles you have is this first part. And then as you have more and more rectangles, what's going to happen to these two terms? N is on the bottom. So what's going to happen if you increase n? N gets bigger and bigger and bigger.
Is it going to get smaller?
Yeah. Those terms are going to get smaller and smaller and smaller, right? Because if you have a big number on bottom, the fraction goes towards 0, okay? And that's important for what we're going to look at in the future here. Okay. So that is, all that work is only half our problem, right? The second half is our upper sum, okay? The upper sum is actually easier, okay? Let's see if we can do this over here, okay? The upper sum is 1 to n, is the same function, but now instead of that complicated expression, we just have I, or 2 over n I, okay, delta x times I, times 2 over n, good, okay, and so plugging that in, that is equal to 2 over ni all squared times 2 over n. So once again, we can factor out an 8 over n cubed, and now we're just left with I squared there, and that is a simple formula, right? So it's 8 over n cubed times n plus 1 times 2n plus 1, good, over 6. All right, oop, that's a bracket. Okay, so finishing off that, you get 4 over 3n cubed times 2n cubed plus 3n squared plus n. For our final answer of 8/3, interesting, plus 4 over n plus 4 over 3n squared. That is our upper sum. Okay, so let's take a look over here at what we got for our lower sum and compare them. This was our lower. Side by side, what is similar, what is different? The only difference between the upper sum and the lower sum is this one little minus sign and the plus sign here. Okay. Again, the 8/3 is the same out front. That does not depend on n. And the other two terms that do depend on n will get smaller and smaller as n increases. But here we add 4 over n, and here we subtract 4 over n. That's the only difference between the two. Okay. Okay, so the previous example can be used to explain very sort of quickly what the difference is between the upper and lower sums and how to eliminate that difference. Okay, so I sort of hinted at it before. How could you get them to be the same? Increase in, because as you increase in, both will equal 8/3. Okay, so by definition, we approach taking the limit as n approaches infinity of the upper sum and the lower sum, and we can apply our good friend, the squeeze theorem, you might remember him, and find that it doesn't matter whether you pick left endpoints or right endpoints, midpoints, or just a random point in each interval. As you take n towards infinity, you will end up with the actual area of this plane. If you set up your sum correctly, and that's pretty cool. Okay, so we are going from summations to which is an approximation. Okay, so summation, which is giving us approximations of area under a curve, to now an exact area. Okay, we by definition say that the exact area underneath the curve is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of ci delta x, where ci is any number within your intervals bounded by delta x. Okay, and this is saying we're going from A to B, so whatever our endpoints are, A and B. And by definition, we're saying that our delta x is equal to B minus A over n, okay, which has a special name. We'll talk about that more in a second here. Okay, so by definition, the area of a region in a plane is given by this expression.